Hello, in this lecture we'll find out the area of the green shape. In the drawing we have a circle. The radius of this circle is 2, r equals to 2. In addition we have also, this is peripheral angle ACB that equals to 70 degrees in its size. And we also have the common extra point, point P. For the common extra point, point P, this point we have two tangents to this circle, tangent AA, tangent PA, that is tangent to this circle here at point A, and tangent PB, that is tangent to this circle here at point B. Again, and our mission is to find out the area of this green shape. Point O is the center of the circle. So we'll join points O and B together by a straight line. What is the definition of line segment OB? Line segment OB starts from point O, that is the center of the circle, and ends at point B, that is the point on the circle itself. This is exactly the definition of a radius. So OB is the radius of this circle that is equals to 2 units according to what is given us in the question. So OB equals to 2 is the radius of the circle. We can implement here rule 1. We repeat quickly on rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So we have in the drawing a circle, and we have tangent AB that is tangent to this circle here at point M. And we have the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can implement rule 1 in our drawing. Why? Because in our drawing we have the radius OA that is drawn to point A, that is the point of tendency of tangent PA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees. Likewise, according to the same rule, rule 1, we have the radius OB that is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. Repeat again on rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle, and we have inside this circle peripheral angle ACB that equals to theta degrees in its size, and this peripheral angle ACB is subtended on this arc RKB. In addition, we have in this drawing the central angle AOB that is subtended on the same arc AB, and therefore according to this rule, rule 13, the central angle AOB will be twice as large as this peripheral angle ACB. And because of the fact that the peripheral angle ACB equals 2 theta, that the central angle AOB that is subtended on the same arc RKB will be equal to 2 theta. We can actually implement rule 13 in our drawing. Why? Because in our drawing we have peripheral angle ACB is equals to 70 degrees in its size and is subtended on this arc RKB. And we also have the central angle AOB that is subtended on the same arc RKB, and therefore according to rule 13, the size of the central angle AOB will be twice as large as the size of the peripheral angle ACB. And because of the fact that the peripheral angle ACB is equal to 70 degrees, therefore the central angle AOB will be equal to 70 degrees times 2, that is 140 degrees, because it is also subtended on the same arc AB. So if we found out that the size of the central angle AOB is 140 degrees. In the next step, we join points O and P together by a straight line. By joining points O and P, we created here two right triangles, the upper right triangle OAP and the lower right triangle, triangle OBP. So in the next step, we will prove that those two right triangles can go into each other. So actually we'll prove that the right upper triangle, triangle OAP, is congruent to the right lower triangle, triangle OBP. So why those two right triangles can go into each other? First of all, side AO in the right upper triangle AOB is equal to side BO in the right lower triangle OBP. They're both the radii of the circle, therefore they are equal to each other. So OA equals to OB. Are both the radii of the circle, that is equal to 2 units, therefore they are equal to each other. In addition, side PO is a common side that belongs to both triangles, so okay, write down that PO equals to itself. It's a common side that belongs to both triangles. Repeat again. Side PO equals to itself. It's a common side that belongs to both triangles. And finally, side PA of the right upper triangle AOP equals to side PB of the right lower triangle, triangle POB, according to rule 2. So write it down. PA equals to PB according to rule 2. So I repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the domain we have a circle, and we also have this common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, all two, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. Why? Because in our drawing, we have the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to all two, they are equal to each other. That is to say, PA equals to PB. So, PA equals to PB according to rule 2. So we actually proved that all the three sides of this right upper triangle PA, all these three sides of the right upper triangle, triangle PAO, are correspondingly equal to all the three sides of the right lower triangle, triangle POB. Therefore, those two right triangles can move into each other according to side rule. So I write it down. So the upper right triangle AOP is congruent. This is the sign of congruent to the right lower triangle, triangle OBP, according to side rule. And from the fact that those two right angles can go into each other, we will derive that those two angles are also equal to each other, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So this is angle AOP in the right upper triangle AOP. And it is equals to this angle. This is actually angle POB or BOP, it is the same. BOP in the right lower triangle BOP. Angle AOP equals to angle BOP. So if we define one of those two equal angles as alpha, then the other angle must be also equal to alpha because they are equal to each other. So if we define angle AOP as alpha, then angle BOP also must be also equal to alpha because they are equal to each other. So from the drawing itself, it is very easy to see that alpha plus alpha equals to this big angle, and this big angle equals to 140 degrees. We already found out that the big angle is equals to 140 degrees here. So can I write down that alpha plus alpha equals to 140 degrees. Alpha plus alpha is 2 alpha, that is equals to 140 degrees. Here we divide this equation by 2, and finally we get that the missing angle alpha is equals to 140 degrees over 2, it is 70 degrees. So this is angle alpha, that is equals to 70 degrees in its size. And this is also angle alpha, this is equal to 70 degrees. In the next step, we'll focus on the right upper triangle, triangle AOP. So in the right upper triangle, triangle AOP, it is very easy to see what is the value of tangent 70 degrees? Tangent 70 degrees in this right angle triangle AOP is equals to AP over AO. Repeat again, in the right upper triangle AOP, tangent 70 degrees equals to AP over AO. Tangent 70 degrees is 2.75. So 2.75 is equals to AP. AP is the missing side, so we leave it as it is. It is AP over AO. AO equals to 2, it is the radius of the circle, so we substitute AO by 2. So it is AP over AO, that is 2. In conclusion, we found out that 2.75 is equals to AP over 2. Here we will multiply this equation by 2. And we get that AP, the missing side AP equals to 2 times 2.75 is 5.5. So in conclusion, we found out that the length of the missing side AP is 5.5. So I write it down in this moment that AP equals to 5.5 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of the upper right triangle AOP plus the area of the lower right triangle POB so actually the sum of the areas of those two right triangles will give us the area of quadrilateral AOBP. So the area of quadrilateral AOBP minus the area of this sector AOB will give us exactly the area of this green shape. So we have to subtract from the area of quadrilateral AOBP, that is the sum of the areas of those two right triangles, the area of this sector AOB. Here, the round line above AOB is the sign for a sector. It means sector AOB, and the square bracket is the sign for the area. So in total, this expression means the area of sector AOB. Repeat again that the sum of the areas of those two right triangles is equals to the area of quadrilateral AOBP, and the area of quadrilateral AOBP minus the area of this sector AOB will be equal exactly to the area of this green shape. So in the next step, I will clarify the concept of sector. What is a sector? A sector is part of a circle. It is a portion of a circle. So the green shape AOB is a sector. Sector A or B. Sector A or B consists of two radii of the circle. We can also define the two radii of this circle as the legs of sector A or B, and also the arc between the two radii, the arc AB, is part of sector A or B. So, in conclusion, we can say that sector A or B consists of two radii of this circle, 1 and 2, and sector and arc AB, that is the arc between those two radii. And the angle between those two radii, also you can say the angle between the legs AO and OB of this sector AOB is angle theta. So what is the area of this sector, sector AOB? The area of this sector AOB is equal to the area of the circle that contains the sector, that is actually pi r square, because the radius is r, therefore the area of this circle that contains sector AOB is pi r square, times the angle between the legs of this sector, that is theta, over 360 degrees. In conclusion, you can say that the area of this sector AOB equals to pi r square times theta over 360 degrees. Okay. So, we found out that the area of the green shape in total, it is equal to the area of the right upper triangle AOP plus the area of the right lower triangle BOP minus the area of sector AOB. Because of the fact that the area, those two right upper triangles can go into each other, they have also the same areas. Therefore, we can substitute the area of the right lower triangle BOP by the area of the right upper triangle AOP, because they are equal to each other. So we'll do it now, and we get that the area of the green shape in total is equal to the area of the right upper triangle AOP plus the area of the lower triangle BOP. So we substitute the area of the lower triangle BOP by the area of the upper triangle AOP, because they are equal to each other. And we have to subtract from the sum of those two areas the area of sector AOB. Repeat again that the sum of the areas of those two right triangles will give us the area of quadrilateral AOBP, and the area of quadrilateral AOBP minus the area of this sector AOB will give us exactly the area of this green shape. Okay, so we have here the area of the right upper triangle AOP plus the area of the right upper triangle AOP is equals to 2 times the area of the upper right triangle AOP minus the area of sector AOB. So first of all, we have to find out the area of the right upper triangle AOP. What is the area of the right upper triangle AOP? We know that the area of any triangle is equal to the base of the triangle times the height to the base over 2. So the area of this right upper triangle AOP equals to the base of the triangle times the height of the base over 2. We choose the base of this right upper triangle AOP is AO, side AO. So the base is AO times the height of the base. The height will be AP. Why? Because the height AP creates 90 degrees with the base AO. So the height is AP over 2. AO, the base AO is equals to 2, so we substitute AO by 2 times AP. AP is 5.5, so we substitute AP by 5.5 divided by 2. So we have here 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we left only with 5.5. In conclusion, we found out that the area of the right upper triangle AOP is equals to 5.5 square units. And the area of the green shape equals to 2 times the area of the right upper triangle AOP minus the area of sector AOB. So 2 times the area of the right upper triangle AOP is 2 times 5.5. 2 times 5.5 is 11. So 11 square units is the area of quadrangle AOBP, and we have to subtract from the area of quadrangle AOBP the area of this sector AOB. So the area of the green shape in total equals to 11 minus the area of sector AOB. So in the next step we find out the area of this sector AOB. What is the area of sector AOB? The area of this sector AOB equals to the area of the circle that contains sector AOB, that is actually pi r squared because the radius is r. So it is pi r squared times the angle between the legs of this sector, that is 140 degrees, over 360 degrees. The radius of this circle r equals to 2, therefore r squared is 2 squared, that is 4. So in total the area of the circle that contains sector AOB is 4 pi times, we have to multiply the area of the circle that contains sector AOB, that is 4 pi by 140 degrees over 360 degrees. So this expression in total, 4 pi times 140 degrees over 360 degrees, is equals to 4.888 square units. In conclusion, we found out that the area of sector AOB in total it is equals to 4.888 square units. In the area of the green shape, the area of the green shape, the area of this green shape equals to the area of quadrangle AOBP, that is the sum of the areas of this triangle plus the area of this triangle, that is 11 square units. So it is the area of quadrangle AOBP minus the area of this sector AOB. And we just right now found out that the area of sector AOB is 4.888, and 11 minus 4.888 is 6.111. And concluding found out that the area of the green shape is equals to 6.111 square units. Repeat again, the area of this green shape is equals to 6.111 square units. Okay, so in the next step I will summarize the lecture. In this lecture we found out the area of this green shape. So in the drawing we have a circle. We know that the radius of this circle r equals to 2. And we also know inside this circle we have peripheral angle ACB that equals to 70 degrees in its size. Peripheral angle ACB equals to 70 degrees in its size. In addition we have in the drawing the common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB. Again, our mission is to find out the area of this green shape. So in the first step, we joined points A and O together by a straight line. Point O is the center of this circle, point B. We join points O and B together by a straight line. Point O is the center of this circle, point B is the point of the circle itself, therefore OB is the radius of this circle, that is equal to 2 units according to what is given us the question. We implemented here rule 1. The radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees. Likewise, according to the same rule, rule 1, we have the radius OA that is drawn to point A, that is the point of tendency of tangent PA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees. In the next step, I actually presented to you a new rule, that is rule 13, and we implemented rule 13 in our drawing. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. I repeat again on rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have peripheral angle ACB that is equal to theta degrees in its size, and is subtended on this arc RKB. In addition, in the drawing we have also the central angle AOB is subtended on the same arc RKB, and because of the fact that the peripheral angle and the central angle are both subtended on the same arc RKB, the size of this peripheral angle will be twice as large as the size of this peripheral angle that is subtended on the same arc. So the size of peripheral angle ACB is theta, therefore the size of the central angle AOB that is subtended on the same arc RKB will be equal to 2 theta. We can actually implement rule 13 in our drawing. Why? Because in our drawing we have the peripheral angle ACB. This is peripheral angle ACB. That is equal to 70 degrees in size, and it's subtended on this arc RKB. In addition, we have the central angle AOB that is subtended on the same arc RKB. Therefore, according to Rule 13, the size of the central angle AOB will be twice as large as the size of the peripheral angle ACB that is subtended on the same arc RKB. So the size of peripheral angle ACB is 70 degrees, therefore the size of the central angle AOB that is subtended on the same arc RKB will be equal to 70 degrees times 2, that is 140 degrees. In conclusion, found out that the size of this central angle AOB is equal to 140 degrees. In the next step, we join points O and P together by a straight line. By joining points O and P, we created here two right triangles. We have the upper right triangle AOP and the lower right triangle BOP. And then we actually proved that those two right triangles can go into each other. Why those two right triangles can go into each other? First of all, side AO is in the right upper triangle AOP is equal to side BO in the right lower triangle BOP. They are both the right eye of the circle, therefore they are equal to each other. Repeat again. OA equals to OB equals to R equals to 2. Okay, in addition, side OP is a common side that belongs to both triangles, so we can write down that OP equals to itself. It's a common side that belongs to both triangles. Here, OP equals to OP is a common side that belongs to both triangles. And finally, according to Rule 2, side PA of the right upper triangle AOP is equal to side PB of the right lower triangle POB. So I repeat quickly on Rule 2. According to Rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing we have a circle and we have also the common external point P. From the common external point P we have two tangents to the circle, tangent PA and tangent PB. And according to this Rule 2, they are equal to each other. That is to say, PA equals to PB. We actually implemented Rule 2 in our drawing. We implemented Rule 2 in our drawing because according to Rule 2, we have here the common external point P. From the common external point P, we have two tangents to the circle, tangent PA and tangent PB. And according to Rule 2, they are equal to each other. That is to say, PA equals to PB. Repeat again. PA equals to PB according to Rule 2. So actually proved that all the three sides of the upper right triangle AOP are correspondingly equal to all the three sides of the right lower triangle POB. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles are also equal to each other. They are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles can go into each other, therefore those two corresponding angles must be also equal to each other. Repeat again. Angle AOP equals to angle BOP. So if we define this angle AOP as alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha is this big angle. Alpha plus alpha is this big angle. And we have found out that this big angle AOB is equal to 140 degrees in its size. Okay? So we can find out that angle actually I found out that alpha plus alpha, that is 2 alpha, equals to 140 degrees. Okay, alpha plus alpha equals to 140 degrees. Alpha plus alpha is 2 alpha, that is equals to 140 degrees. Here we divided this equation by 2, and finally found out that the missing angle alpha equals to 140 degrees over 2, that is 70 degrees. So this is angle alpha, that is equal to 70 degrees inside, and this is also angle alpha, that is equal to 70 degrees. In the next step, we focused on the right upper triangle, triangle AOP. On the right upper triangle AOP, what is the value of triangle 70 degrees? From the moment it is very easy to see that in this right triangle AOP, triangle 70 degrees equals to AP over AO. Again, triangle 70 degrees equals to AP over AO. So in the right triangle AOP, triangle 70 degrees equals to AP over AO. Triangle 70 degrees is 2.75, and it is equals to AP. AP is the missing side, so we leave it as it is, over AO. AO is the radius of this circle R, that is equal to 2, so you can substitute AO by 2. Here we substitute AO by 2. In conclusion, we found out that 2.75 equals to AP over 2. Here we multiply this equation by 2. And finally we found out that the missing side AP equals to 2.75 times 2, that is 5.5. In conclusion, we found out that the length of side AP, the missing side AP, is 5.5 units. Okay? I repeat again that our mission is to find out the area of this ring shape. So what is the area of this ring shape? From the drawing, it is very easy to see that the area of the ring shape equals to the area of the upper right triangle AOP plus the area of the lower right triangle BOP. The sum of the areas of those two right triangles will give us the area of quadrangle AOBP. And the area of quadrangle AOBP minus the area of this sector AOB will be equal exactly to this area of the ring shape. So repeat again, the area of the ring shape. The area of the ring shape equals to the area of the upper right triangle AOP plus the area of the lower right triangle BOP. The sum of the areas of those two right triangles will give us the area of this quadrangle AOBP, and then the area of quadrangle AOBP minus the area of this sector AOB will give us exactly the area of the ring shape. So the sum of the areas of those two right triangles is the area of quadrangle AOBP. So the area of quadrangle AOBP minus the area of sector AOB is equal exactly to the area of the ring shape. Then I presented to you the concept of sector. What is a sector? A sector is part of a circle. It is a portion of a circle. So this is a circle, and the ring shape AOB that is part of this circle is a sector, sector AOB. Sector AOB consists of two radii. The first radius AO, and the second radius is BO. You can also say that the two radii are the two legs of this sector. So the first leg is AO, and the second leg is BO. And sector AOB is also consists of arc AB, that is the arc between the two legs, or the arc between the two radii, AO and BO. And it also consists of angle theta, that is the angle between the two legs, AO and BO, or angle between the two radii, or the two legs of this sector AOB. So what is the area of this sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is pi r squared, times the angle between the legs of this sector, that is theta, over 360 degrees. In conclusion, we found out that the area of the sector AOB, the green sector AOB, equals to pi r squared times theta over 360 degrees. Okay. So the area of the ring shape equals to the area of the right upper triangle AOP plus the area of the right lower triangle BOP minus the area of sector AOB. We have already found out that those two right triangles can go into each other, and therefore they have also the same areas. Therefore, we can substitute the area of this right upper triangle BOP by the area of this right upper triangle AOP because they are equal to each other. Okay, again, you can substitute the area of the right lower triangle BOP by the area of the upper right triangle AOP because they are equal to each other. We actually did it. So the area of the green shape in total will be equal to the area of the right upper triangle AOP, and the area of the lower triangle BOP is equal to the area of the upper right triangle AOP. So we substitute the area of the lower right triangle BOP by the area of the upper right triangle AOP minus the area of sector AOB. The area of triangle AOP plus the area of triangle AOP is 2 times the area of triangle AOP minus the area of sector AOB. So then we actually found out the area of the right upper triangle AOP. What is the area of the right upper triangle AOP? Actually, the area of any triangle equals to the base of the triangle times the height to the base over 2. So in this right triangle AOP, we choose the base as AO, and the height to the base is AP. Again, the base is AO and the height to the base is AP. AO equals to 2. So we substitute AO by 2, and AP is equals to 5.5 units. Here AP equals to 5.5 units, so we substitute AP by 5.5 divided by 2. So we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we left only 5.5. In conclusion, we found out that the area of the upper right triangle AOP equals to 5.5 square units. And we have to multiply the area of the right upper triangle AOP by 2. So it is 2 times 5.5, that's 11. In conclusion, we found out that the area of this quadrangle AOBP equals to 11 square units, and the area of the right upper triangle AOP, that is 11 square units minus the area of this sector AOB, will be equal exactly to the area of the green shape, that is the area that we are looking for. Okay, again, that the area of quadrangle AOBP, that is 11 square units minus the area of sector AOB, will be equal exactly to the area of the green shape. So in the next step, we found out the area of sector AOB. What is the area of this sector AOB? The area of this sector AOB equals to the area of the circle that contains the sector times the angle between the legs of this sector, that is 140 degrees over 360 degrees. Repeat again, the area of sector AOB equals to the area of the circle that contains the sector, that is pi r square, times the angle between the legs of the sector, that is 140 degrees over 360 degrees. So pi r square is pi times the radius square. The radius of this circle is r, that is equal to 2. So r equals to 2, therefore r square is 2 squared, that is 4. So in conclusion, we found out that the area of the circle that contains the sector is 4 pi times 140 degrees over 360 degrees. That is the total area of sector AOB. So this expression in total 4 pi times 140 degrees over 360 degrees equals to 4.888. In conclusion, we found out that the area of sector AOB equals to 4.888 square units. The area of this sector AOB equals to 4.888 square units. So the area of quadrangle AOBP, that is 11 square units, minus the area of this sector AOB, that is 4.888 square units, will give us exactly the area of this green shape. Again, the area of quadrangle AOBP, that is 11, minus the area of sector AOB, that is 4.888, will give us exactly the area of the green shape. So 11 minus 4.888 is 6.111. In conclusion, we found out that the area of this green shape is equals to 6.111 square units. Okay, thank you very much.